Why, hello, folks. Dr. Picklestein here, and today I want to talk about heat capacity. Now, in case you didn't know this, my actual given name is not Dr. Picklestein. It's just the fun name I use when I do demonstrations and do science around the Idaho area. But I am also a professor, and my name is Henry Charlier, and I teach chemistry at Boise State University. Now, one of the topics that we cover is heat capacity. And we talk about heat capacity in general chemistry, college chemistry, as we kind of refer to it that when you're looking at a given substance or an amount of a substance, it's the amount of energy it takes to raise that temperature of that substance. And so if you find a substance, let's say you want to raise the temperature of 1 gram of a substance by 1 degree Celsius, uh, you can measure the energy that is needed to do that. And actually, we have a name for that. It's called specific heat capacity. It's the amount of energy in the form of heat that it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. And and so if it absorbs that amount of heat, then if you were to lower the temperature, it would also release that amount of heat as well. So I'm going to do an experiment, and you're going to see this, and we're going to see how different materials, and I got 3 metals in this case, each one has a different heat capacity. I will fill you in on the details of the materials a little bit later, but in essence, each one has a different specific heat capacity, so they can hold more energy when you raise the temperature. They absorb more energy or different amounts of energy than one another. And then when I allow that energy to be released and transferred to its environment, in this case, you're going to see it's going to be a piece of wax, we can see how the ones with greater heat capacity hold more heat and can melt more wax than the materials that have a lower heat capacity and don't have as much heat stored. So let's take a look at that. I have 30 grams of 3 different metals. The first, the tallest one, is aluminum. The darkest one is zinc. And the short, light one is tin. Each of these rods has a 1/2 inch diameter. So in terms of heat capacities, specific heat capacities, aluminum is 0.9 joules per gram per degree Celsius. Zinc is 0.3, 87 joules per gram per degree Celsius, and tin is 0.210 joules per gram per degrees Celsius. So we're going to do an experiment where we're going to heat up each of these rods to the same temperature and then let them release their heat into some wax, and we will measure how much wax gets melted as the heat is transferred to the wax, and we will make a comparison between each of these rods. So one way that we can ensure that they all have the same temperature is to heat to boiling, and in Boise this particular day it was 98.9 degrees Celsius. So the wax that we will be using is wax that I have obtained from Amazon. It's very thin wax, and it is used for dentures. It's called base plate wax, and it's fairly thin, and you can see the rig I have here where I have some guiding lanes where I'm going to put each of the hot pieces of metal, and then I'm going to let them melt their way down and measure the distance that they travel as they melt, which in principle should be related to how much heat that they have um, stored. And that, of course, as I mentioned before, should be related to the heat capacity. The more the heat capacity, the higher it is, the more heat it should contain and then therefore release to the wax. So the tin, for instance, had the least amount of heat capacity. So if I let this tin rod go and we're just letting it drop down until it reaches its room temperature, until it's no longer, it gets rid of all of its heat, then we'll measure the distance that it melts down. And of course, we'll do the same thing for zinc. And you can see zinc here is there. And remember, these all have the same number of grams. They just have different densities. And that's why some pieces are bigger than others, like aluminum has the lowest density. So it actually, the same number of grams will require a taller column that has that ½ inch diameter. So you can see how they're melting their way down and dropping down just as we would have expected. Now I'm going to add the zinc, not the zinc, the aluminum, and we're going to do that again. And it's kind of tricky because it's taller, so I'm going to have to guide it a little bit, as you can see, and trying not to touch it that much at all, just to make sure that I do not release heat to the forceps that I'm using there. And so you can just watch how this moves its way down, and so far they're melting the wax, moving down as they're getting rid of the heat that they've stored. And just as a reminder, the tin on the right has the lowest heat capacity. The zinc on the far left has the next highest heat capacity, and then the aluminum has the highest of all. So as I watch this go through and melt the wax, the prediction is the one with the highest heat capacity has the most heat and therefore should melt the most wax and drop furthest down onto the wax plate and melt the most wax. So let's watch and see if that's in fact what happens. So in this case, I sped it up so we didn't have to watch for the next 5 minutes or whatever it was. I think it was around 5 minutes, so I sped this up quite a bit so we can kind of see it go to the end. And then it's time to make my measurements. And so in order to do that, I use the calipers that I have off on the left there. And I made the measurements in millimeters. And so you can see how they've all gone down. And I had to peel off. You can see how it melted into the wax a little bit, and so I had to peel that off to find out where the actual edge of the column was. And then I made use of the calipers to make the measurements that were required. So as I make these measurements, I measured tin to be 17.7 millimeters with the calipers. So then from the tin, I went on to measure the zinc, and I got, let's see, I got 30.189 millimeters. So that's how much wax was melted there. And then I'm going to include this a little more information here so you can kind of see how I align the calipers to get to the edge of the metal and from the top of the wax. And in the case of aluminum, I got 51.05 millimeters. So I then repeated that same study 3 additional times. So I had a total of 4 measurements for distance. As you can see, I have distance 1, 2, 3, and 4. And then from that I computed the average of all 4. And you can see where I put the average plus the standard deviation in that column. Then I went on and did a comparison, and hopefully you can see this comparison. I noted that as the specific heat capacity increased, going from tin to zinc, then to aluminum, the distance traveled also went in the same direction. It increased in each case. And so as the specific heat capacity rose, so did the distance that was traveled. Presumably that's because the thing with the greatest heat capacity melted the most wax, which is what we predicted. So then I did a plot of the data, and I plotted distance traveled against specific heat capacity. And that just again shows in a graphical manner that as the heat capacity increases, so does the amount of wax, or the distance traveled through the wax. So this confirms the idea that the item with the most heat capacity holds the most heat and therefore melts the most wax. So hopefully you got something from this, maybe gained extra appreciation for what heat capacity is, and how it helps define the properties of a given substance. Signing off, this is Dr. Picklestein.